Hello, hello. Am I audible, students?
Yes, sir.
Sir.
Mithilesh, please check. वॉइस नहीं आ रहा मतलब मैं बात कर रहा हूँ स्टूडेंट्स तो रिप्लाई नहीं कर रहे थे मुझे नहीं सुनाई दे रहा था अब सुनाई दे रहा है नहीं कैमरा कुछ हिला क्या था ओके चलो ठीक है आई मैनेज okay so good evening students am I audible to you?
Good evening, sir. It is audible.
Yes, sir.
Thank you. Okay. So yesterday we were doing the DC electric conductivity of metals. Okay, and today we are going to do important law. Okay, that is called Whitman French Law. So this law was given in 1853. Okay, and this is an empirical law. So what do you mean by empirical law? Empirical law means this law is based on of various experiment measurements. Okay, so when they measure experimentally the thermal conductivity and the electric conductivity of metals, okay, and then by measuring these two parameters, okay, the Whitman French concluded that, okay, so first of all, this is the empirical law. Okay, and this law says the ratio, okay, of thermal conductivity to electrical conductivity okay, depends linearly on temperature T. Okay, what that mean? So if I take the ratio of thermal conductivity is being measured by a symbol is K, kappa type K, and you know electrical conductivity signal symbol is sigma. So if I measure K by sigma, okay, so this constant is proportional to temperature. Okay, and if I take the ratio of these two, K by sigma T, so this is equal to constant. And all of you may be knowing this.
Sir, you are not audible.
Sir, you are not audible, sir.
Okay. So now, if I want to calculate this, I need to calculate this thermal conductivity. Okay. Once I know thermal conductivity, I know the expression for electric conductivity, which we calculated yesterday. Okay. And then we can find the ratio and we can confirm this law. Okay. So let us calculate the thermal conductivity using the classical law of free electron theory, what we have know. Okay. So I'm erasing this one. Okay. Now, first of all, before calculating thermal conductivity, okay, we should know what do you mean by thermal conductivity. Okay, so let me give the definition of thermal conductivity. Okay, so thermal conductivity is nothing. Thermal conductivity is K is defined by rate of flow of heat per unit time per unit area. Okay, the rate of flow, that is Q by A T. Okay, the rate of flow of Q is heat, rate of flow of heat per unit area per unit time and per unit temperature gradient, per unit temperature gradient, delta T upon delta X or dt upon dx. So this is the formula for your thermal conductivity. Okay, this K is your thermal conductivity.
Sir, can you repeat the definition once more?
Yeah. So the rate of heat flow, okay, per unit area, per unit time, for per unit gradient of temperature, per unit distance gradient of temperature. Okay. So you can see here Q is what? Heat flow. T is a time. So heat flow per unit time, per unit area. So it is like a current. Right? It is like current. So I write this current by JQ, thermal current. This is my thermal current, and this is what? Temperature gradient per unit temperature gradient. Delta X, delta T upon delta X. Okay, temperature varies with distance. So this is temperature gradient. Okay, so you can also write this as a dt upon dx. This is the definition of thermal conductivity. Now, if I want to, now you know this definition. Okay, now I need to calculate thermal conductivity. Okay, so let us calculate thermal conductivity. Okay, and if I write this law, okay, this law also can be written jq equal to minus k dt upon dx. Okay, so this form you should remember. Thermal current is equal to minus thermal conductivity and dt by dx is the temperature uh, gradient, and this law, this equation is called Fourier law of heat conduction. Okay, Fourier's law of heat conduction. Okay, okay. So now once you know the definition of thermal conductivity, okay, we can proceed for thermal current. Okay, JQ is thermal current density. Okay, because this is what current Q by T is current, I dq by dt, current per unit area, that means current density. Okay, this is thermal current density, thermal current density. Okay. Now let us do the calculation part. Okay, so I'm erasing this one. So this is very pretty simple derivation. Okay, you might have encountered in statical physics also. Okay, so now suppose I have a rod of sample. Okay, because we need to calculate heat flow per unit time per unit area. Okay, Say I have a rod of metal. Now here is stream. Okay, we are giving stream or we are giving heat flow. Okay, this is the direction of heat flow. So this side of the rod, I am flowing heat. Okay, so obviously this part will be my hotter, this side will be hotter compared to, and this side will be cold, cooler compared to that side. Okay, so obviously when I'm supplying heat here temperature will increase, and this all temperature flow from this side of, so due to convection, from this side to this side. Okay, and you have to remember that in solid, all the heat, now heat can be transported by two manners. Okay, one due to is lattice vibration, and through the atomic vibration, and the second is due to electrons. Okay, so there's a two methods of transporting energy in solid. Okay, one is lattice through atomic vibration, and other is through your electrons. Okay, now in the case of metal, okay, almost all the heat is transported through the electrons. Okay, while if you see the insulator like diamond, okay, insulators, so where there all the heat is transported through the atomic vibrations. Okay, so then this is the important point you need to remember. Okay, that in metal, okay, electrons are principal carriers, okay, carriers of heat energy. Okay, principal carriers of heat energy. This is the important point. So whatever heat is there, that it will be transported through the electron. Now how they transport the heat? So suppose we are supplying energy here, we are applying temperature here. Okay, and this portion we have electrons. Okay, the electron, we know the electrons are colliding with the lattice. Okay, I told you in field theory there is no electron interaction. Okay, only electrons are colliding with your scattering centers. So when I'm giving energy, this energy is taken by the electrons, and electrons, there are lattices. Okay, here we have lattices, and they collide with the lattice, and they transfer this energy. Okay, again they take energy, and they get collide, and they transfer all the energy to the centers, the scattering centers. Okay, so what will happen? Heat will flow from hotter end to cooler end. Okay, I hope what I'm saying is clear to you. Okay, are you getting what I'm saying? Are you getting what I'm saying? Okay, the heat is passed by electron to the scattering centers. Okay, electron will carry heat, and they'll collide with the lattice, and lattice will get heated. Okay, so this all the process happen only through the electrons. Okay, so this you have to remember. Now I need to calculate the thermal conductivity of this rod. Okay, how it is transported. Okay, so now obviously there is a temperature gradient. Okay, so let us say this point is, okay, this point is A, this point is B, and this point is C. Okay, and these all points are exactly lambda distance away. Lambda is what? Mean free path. Lambda is what? Mean free path. Now, why I'm taking these distances as a lambda? Can anyone tell me? What did we discuss?
The distance between two collisions.
Yes. Okay. And once they collide, electron will lose all its energy, isn't it? Okay. So whatever energy electron is here, okay, exactly after traveling lambda distance, this energy they will pass here in this position, whatever atoms are there. Okay, similarly whatever atoms are here, because they lose all the energies. Okay, so whatever energy here, so they will travel lambda distance mean free path, and they will lose the energy here. Okay, now I have to calculate heat passes through here. Okay, so this is here my hotter end, and this is my cooler end. Okay, so I need to calculate how much flux is passing, how much heat is passing. Okay, so let us say the temperature of this point is T. Okay, so temperature of this point should be greater than T or less than T?
Greater than.
Greater than this. So the temperature is T, and what I can write? because the temperature gradient is delta. Say assume the temperature gradient is delta T by del X. Okay, and this is lambda distance away. Okay, so this is this portion is higher temperature. Similarly, this portion is a lower temperature, so I can write the temperature T. Okay, this is a cooler temperature T minus delta D upon delta X into lambda. Okay, can I write like this?
Yes, sir.
Okay, so this is a temperature gradient. Temperature increasing with here this side temperature more, temperature decreasing this side increasing, and this side decreasing. Okay, so here we have a lambda del, this is temperature gradient and this is a decreasing temperature. Okay, so now we know the temperatures. Okay, so once I know the temperature I know that from the kinetic theory of gases that energy also depend on temperature. So this portion, the electron which are in this portion, they have a higher energy. Okay, and their energy can be written as what? E plus d by dx into lambda. Say this portion of electron has energy E, and this part of the electron have energy what? E minus delta E upon delta X into lambda. Okay, because the energy depends only on temperature in classical theory, isn't it? So the temperature is higher here, energy is higher here. Okay, so your temperature gradient, so there should be energy gradient. Okay, so this portion of energy. Now I need to, now you know the classical theory. Okay, now electron is moving from here to here. They are moving here. Now I want to know how much heat is passing through this this portion of B, this from B. Okay, per unit area, per unit time. So electrons are moving here also, electron are moving here also. Okay, so now you know the now from according to kinetic theory of gases. Okay, according to kinetic theory of gases. Okay, kinetic theory of gases, the flux passing in any direction per unit area per unit time is equal to what? What is the value of flux? You've done this in thermodynamics. The number of electron, okay, or number of flux, the number of electron passing in any direction, okay, per unit area per unit time, that is flux time, okay, is equal to what? Anyone? What is the value of flux?
Number into velocity.
Very good. Okay, so number into velocity, and that is not, that is equal to 1/6 number into average thermal velocity. Okay, so this portion you've done in your thermodynamics. Okay, if you're not done, okay, you let me know. So I'm giving this derivation. I'm not deriving this part here. Okay, so this part is your homework. Okay, you need to send me this homework. Okay, if if you're not able to do, then I will do the derivation. Okay, so now you have the number. Okay, so n is the what? Number of free electron density. Okay, n is the number of free electrons, okay, per unit per cubic meters. Okay, per density per cubic meter. And V is what? V is your average thermal velocity. Okay, average thermal velocity. Okay, so now you know the flux and you also know the energy. Okay, so the electron which are this side lambda distance away, they have this much energy more, and the electron which are this side, they have this much energy less. Okay, both are passing. Okay, these people have a, in their pocket they have heat. Okay, more heat compared to them. This portion of electron, they have a lesser heat. Okay, that's so I need to calculate net flux, how much net energy is transported. Okay, so let me calculate the how much current is flowing, thermal current is current density is flowing. Okay, so if I want to write the expression for thermal current, okay, J net, okay, the net heat the net heat transferred, okay, JQ, okay. So JQ will be what? You have this 1/6 NV, okay, and then you have what? Then you have this d by dx, d by dx. This more this electrons are giving energy, this much energy, extra energy, okay, and then minus, okay, minus, and there's the cooler these are the colder electrons, okay, which have energy what? 1/6 n. Again V is minus V del E upon del X lambda, okay. Now calculate what is the total energy, total heat flow. Total heat flow will be what? 1/6, and this will become plus 2/6. So this will become what? 1/3 n V bar lambda and d by dx, d by dx. So this is my JQ, okay, and I already know what is JQ formula already I know in terms of thermal conductivity. I can compare these two expressions, okay, and I can equate these two equations, and I can find out what is the relation. Say this is the equation B, okay, and the Fourier law, what I written earlier, you can put the equation A, and you can compare these two equations, okay. So once we compare these two equations, this derivation is not important, okay, the result is important, okay. So if I compare this J cube on both sides, so I can write, okay, 1/3 and V bar lambda d upon dx equal to what? Minus k dt upon dx, isn't it? Okay, can I write or not like this or not?
Yes, sir.
Now just, and if you want, if you're comparing only magnitude, okay, you can remove this minus sign because that is only sign convection, okay. So now we have the expression. Now you can calculate delta D K value from this equations, okay. So if I calculate now the value of Q, okay, so I know this is 1/3 and B bar lambda delta E upon delta X. I can write delta T upon D and delta T upon del X, okay. So this will give me delta T upon del X, okay. So delta T upon delta is cancel, okay. So I will be having the K value is what? 1/3 and V bar lambda del E by del T, okay. And del E by del T is what?
Work,
dq by dt is what? This temperature.
current,
current, sir.
heat current,
Heat dq by not time. I'm not telling time, temperature.
Specific heat.
Specific heat. Okay. This is specific heat of what? One electron. This is specific heat. Okay. Del E by del T, energy versus again temperature. This is your specific heat of electron. Okay. So I can write this is electron. Okay. Now here is the problem. Okay. As soon as I write the specific heat, and we know the calculation of specific heat is wrong. When we use classical theory, I told you the what we are calculating specific heat, that is not a correct expression. Okay, but they are again using this classical expression. So what they will able to derive the law, but there the constant Lorentz factor, they that will not be agreement in the theory. Okay, sorry, experiments. Okay, so now I have the expression for this thermal conductivity. Okay, now let us simplify this more. Okay, now I know this V is the average thermal velocity, which is equal to what? Yesterday we have seen that is from, I'm using only kinetic theory of gases. Okay, in free electron theory. So I know the V is this your 3 kBt upon M. Okay, and what is the value of CV? Can anyone remember?
3/2R.
So yesterday we have seen the CV. I have written 3/2 Na kb, that is 3/2 R. But that specific heat is of what? Na electrons, molar specific heat.
Yes.
Here we have only one electron. So 1 electron, for 1 electron CV, this is equal to what? 3/2
kb.
3/2 kb. Okay. Now just put these values here and see what expression we are getting.
सर V average 8 kBt by pi m होगा ना, रूट ओवर।
नहीं, काइनेटिक थ्योरी से कल हमने क्या देखा था? हाफ mv स्क्वायर।
सर वो तो RMS वेलोसिटी।
हाँ, तो उसी से जो हमने निकाला था, ओके, v निकाला था हमने, दैट इज व्हाट 3/2 kBt था ना। ओके, इसी को यूज कर रहे हैं हम लोग, इसी को यूज कर रहे हैं हम लोग, v स्क्वायर 3/2 kBt अपॉन m को, इसको ही यूज कर रहे हैं हम लोग। ओके, सो
ओके,
VRMS, you can say VRMS. Okay, now you can put this value here. Okay, you can put these values here, so I can get what K. The expression for K will be 1/3, and I have this 3 kBt m. Okay, and then I have a lambda, and then I have a CV, that is also again 3/2 kb. Okay, so this is the expression. It's not a simplified expression. Okay, let us solve this more. Okay, so now this, at least we can cancel out this 3, so I can have half and 3 kBt upon m. Okay, and kb1 kb is outside. Okay, now this is the thermal conductivity. What about the electrical conductivity? Can anyone remember what is the formula we used yesterday for electrical conductivity? Anyone
Sir,
remember?
with lambda, there is
Yesterday we check it. We use Ne square lambda upon
M.
3 kb. Okay, 3m kbt. Have you written yesterday? We have done or not done this one?
Yes, sir.
Okay, because we have used this Ne square tau by m. Okay, and when we put the value of tau, okay, tau was what? Lambda by v. So we got this expression yesterday. Okay, now you have this expression, your expression looking like something will cut down. Okay, and you can get some simple expression. Okay, so you have now this expression, say this is your equation C, and this is equation D. Okay, you can divide those two quantities and find out whether we are able to derive the formula Whitman French law or not. Okay, so if I divide K by sigma, okay, so K is my half and KB. Okay, 3 kBt. Please check the calculations. Okay, if some mistake, then I have to go again back. Okay, the n here
Sir,
lambda.
lambda is there, sir.
Lambda is there. That's why I asked. No? Lambda. So we have here K, now n e square lambda. We have 3m kBt. Okay. Three m. This m is here. Km is here down. Okay, and here electric conductivity also you have m down. N is square lambda 3m kBt. Okay, solve it and tell me what is coming.
3k square t by 2e square.
Okay, so lambda will cancel, n will cancel. Okay, and if we saw this one,
M will also cancel.
m will also cancel. Okay, so this should come 3/2 t kb, okay, upon e square. Are you getting this one?
Yes.
Okay, So this is K sigma upon 3 by 2 T. And if I simplify it further, I can write simple law. So this become what? 3 by 2 KB upon E square. Okay. And this is, he told, this is the Lorentz number. Okay. And this is what? This is your Whitman French law. Okay. So at least we are able to derive the Whitman French law here. Only the difference will come in the constant value. Okay. So this is your Whitman French law. So using classical theory. Okay. Whitman French law. Okay. Now this is your empirical law. Okay. So empirical law means what? If this is an empirical law, okay, then you should know experimental measure values. Okay. So if I want to calculate now experimental measured values, okay, so let me give me some data. Okay. So if you solve this one here, okay, here this L 3 by 2 K. So here L 3 by 2, you can put the values here, and if you solve this one, it will come out as 1.12 into 10 raised to power minus 8, okay, watt omega Kelvin inverse. Okay, this value will come out if you put the values here. Okay, now let me give me some experimental value. So for copper, okay, so if I take copper, okay, at 20 degrees centigrade, okay, that is 293 Kelvin. Like I am just not changing temperature what we used yesterday, the same temperature I'm using here. Okay, so that there should not be any confusion. Okay, so if you use this value for we use this temperature, and at this temperature yesterday I told you what is the value of resistivity for copper. Okay, so value of resistivity for copper at this temperature is 1.72 into 10 raised to power minus 8 ohm meter. Okay, and similarly if I take the thermal conductivity, so you can inverse to find, you can inverse it to find out conductivity. So and if you put the KT values, that is 386, this experimental measure values. Okay, K inverse. Okay, now if you calculate at this temperature the ratio of K by sigma T, okay, L, so L comes out 2.26 into 10 raised to power minus 8, okay, omega K power 2. Okay, K power 2 is K inverse or K power 2 inverse, maybe inverse. Okay. So now you can see that there is a deviation, okay, but that deviation is not that much. Okay, only this is the actual value of experimental value is twice of this values. Okay, so there is only difference of factor of 2. Okay, is coming out. Okay, although what we used the specific heat which is 100 times than original values. Okay, but here the expression we are getting only the difference of twice. Okay, and the difference when we will see, when I will calculate the specific heat using the quantum theory, then we will see why this factor of 2 is coming. Okay, that time we will see why, what was the problem. The fundamental problem was that we are using all the electrons. Okay, in classical we are using all the electrons, okay, for electric conductivity as well as thermal conductivity, and in reality only the electron which are near the Fermi energy, when you solve our quantum theory, then we'll see only the electrons which are near the Fermi energy, okay, they only contribute to both specific heat and electric conductivity. So these issues will be solved when we use this quantum field theory. Okay, so this is, okay, so this is not this is actual value. Okay, and this value is not agreement, not in agreement with experimental results, because this is the empirical law, experimental values. Okay, this law itself is derived based on experimental measurements. Okay, and this is not, and for almost all the metals this law is satisfied, this value ratio is satisfied. Okay, this is the one part. Okay, and we'll see what are the problem when we'll solve the quantum electron theory. Okay, so this part is finished. Okay, now let us discuss second property to Whitman. So we are able to tell something about electrical conductivity. Okay, we have derived Ohm's law, we have derived with Whitman French law. Now we are going to derive your Hall effect. Okay, so give me 2 minutes. Okay, now put the heading Hall effect. Okay, now Hall effect, I hope all of you know. Okay, all of you know what is Hall effect. Okay, so can anyone tell me what is the Hall effect? At least definition. Okay, so now the geometry what I'm going to make, okay, for Hall effect. Okay, please look at that carefully. Okay, that will help you in your research also. Okay, when you do PhD and when you do some Hall effect measurements, okay, that time you should remember what I'm drawing now. Okay, this is Hall effect. So what is Hall effect? Anyone? What is Hall effect? Nobody. Okay, so suppose I have a sample, a metallic sample. It can be semiconductor also. Okay, now if the sample, if I apply magnetic field, okay, so I have this sample, say this sample length is say L is a length. Okay, say the breadth of this sample. Okay, okay, so thickness of the sample, say you have T thickness, or you can put it on W also, and the width of this sample is B. Okay, so this geometry you need to remember always. Okay, this thickness, let me make it a little bit smaller. Okay, so it looks a thinner sample. Okay. So this is T, length is L. Now suppose I am flowing current. Okay, in the current in this sample. Okay, suppose in this I'm applying a voltage here. I'm applying a voltage here. Okay. So the current will flow in this direction, and the movement of electron will be what? The movement of electron will be opposite the direction of electron. So my electrons are moving in this direction. Okay, so I am flowing current. Okay, and perpendicular to this I am applying a magnetic field. Perpendicular to the sample I am applying a magnetic field. Okay, so say my this out of the paper direction is magnetic field. Okay, or of sample. So this is my x direction, and say this is my y direction, and this is my z direction. Okay, so my sample length is in x direction, the breadth is in y direction, and above the sample I am applying magnetic field. Okay, now once I apply a magnetic field, okay, now because current is flowing, and the current is flowing, okay, current is flowing in this direction. Okay, this is the flow of current I, but electron is moving in this direction. So now what do you expect? What do you expect?
Sir, here electron is moving opposite to current.
So electronic charge is moving, and I'm applying a magnetic field. So what do you expect?
Lorentz force.
Lorentz force. That's what I'm asking. Na? Anywhere there is a charge is moving, and you're applying magnetic field, so it will experience Lorentz force. Okay, and what is the value of Lorentz force?
Q into V cross B.
P cross B. Q is what? Electron charge. V is what? Velocity of electron. Velocity of electron. Okay, and it is in which direction? Minus x cap. B is in what? Z cap direction. So what will become? Minus minus plus in x cross z. X cross z is what? Minus y cap. So you get E V B. Direction of force is what? Minus y cap, isn't it? Are you getting what I'm doing here? Whenever a charged particle is moving, okay, the electron is moving in x direction, minus x direction, minus x cap. So its velocity I can write v x into minus x cap or v into minus x cap. Okay, b is what? B is in z direction, so z cap, and q is electron charge. So the direction of force will be what? In minus direction. That means what will happen? All the when we apply magnetic field, all the electron will move in this direction. Okay, so when they move this direction, what will happen? This part of the surface, okay, where is we have this one minus y direction. Okay, this is my sample. Let me show my sample. This is my sample. Okay, I am flowing current here. My electron moving this direction, minus x. I'm applying a magnetic field. Okay, then because of this magnetic field, the force is in minus y direction, this direction. So my all the electrons going this surface. So all the electron will get piled on one surface of this surface. Okay, and here there will be because electrons are moving here, you have plus charge here. Okay, so now a voltage will develop. Okay, and this voltage, okay, which voltage is developing in these two phases, this phase and this phase, that voltage is called what? Hall voltage. Okay, this voltage is called what? Hall voltage. Okay, that means now you have electric field. Okay, now if you see this electron, so electron, there is a Lorentz force QBB. Okay, and now because of piling of electron, okay, here electrons are depleted and here electrons are excess. So in these two portions and in this planes or in this sides, you'll get the voltage, and that voltage is called a Hall voltage. And because this Hall voltage, there will be electric field that is called Hall electric field, and that will apply force on this one QEH. Okay, so so that means there will be a steady state. Okay, it is not that always your electron will keep moving here. Okay, because electrons are moving and your electrons are getting piling up one position, and electric field is developing in this side direction. This electric field what to do? It will balance this Lorentz force, and when these two forces are equal, that time the flow of electron will stop and you will get some fixed whole voltage. Okay, so now okay, so now if you give connection to 2 points connection here, if you do 2 point connection here, you'll get voltage. Okay, now just look carefully what I'm saying here. Now you have this sample. Okay, you are applying voltage. Okay, so my one point is there and one point is there. If I want to measure the voltage, what will the voltage across these 2 points? What will the voltage? If this is my plane, okay, these 2 points are in the same plane. These 2 points. If I'm measuring voltage, how much voltage will come? These are equipotential surfaces. If I'm applying sample, they are equipotential surfaces. If I do not apply magnetic field and same plane, if you get two contacts, they are in equal potentials. So voltage drop will be 0. Are you getting my point or not?
Yes.
Okay. And similarly, if you have this point and you have one point here, not same plane, then this point is here, then there is a voltage drop. So whenever you apply voltage to a sample, you get potential difference here to here. Here to here potential difference. So here to here also potential difference in these planes. But if these 2 points lie on same plane, here and here, then this is an equipotential surface. Then there is no voltage. Okay. But when you apply magnetic field, you are getting voltage. That is called Hall effect. Okay. So when you do experiment, you need to take care. You first of all, before performing this experiment, before applying magnetic field, you need to make sure that your voltage drop, what the context you are giving, okay, across those contexts, voltage drop is 0. Okay. Once the voltage drop across this point 0, then only you can apply magnetic field, then only you get Hall voltage. Otherwise, you will get error. Are you getting what I'm trying to say? So suppose I've given you sample, you applied current, you apply magnetic field, and you give context, and so you get some voltage, and then say, oh, I got Hall voltage, my sample is showing Hall effect. But that is not correct. Okay. Before to start this experiment, you need to make sure the points what you're giving here, okay, that is null. That is a null voltage. You have to apply voltmeter in this context, and you check that voltage should be 0. If this voltage is not 0 in this context, if you're not able to put the context in the right position, then you have to do later you have to do correction. Whatever voltage, Hall voltage coming and this voltage coming, you have to subtract or add whatever depending on sign, and then you have to do correction. I hope you people have done the experiment, Hall effect experiment in your laboratory. Okay. Now if I now suppose these 2 points are not in same plane, they are different positions, and I might keep on increasing the voltage. So what will happen? This voltage drop keep on increasing, but that is not a Hall voltage, that is ordinary drop voltage. Okay. Are you getting what I'm saying? If I don't apply any magnetic field here, okay, and I have a sample, if I don't apply any magnetic field and I have a sample, I'm applying battery voltage, okay, because of this voltage, there will be voltage drop. So any 2 points here or here, if there is a gap between this point, there will be always voltage drop. And if you increasing the voltage, this voltage drop will also increase. Okay. But if these 2 points are in same plane, so metal, so even though you are increasing voltage, these 2 points will always show you 0 voltage, because they are on the same they are equipotential surface. Okay. Now, but when you apply magnetic field, okay, so then this equipotential surface also, then a voltage will develop. That voltage is called Hall voltage. Okay. Now this Hall voltage, what it will do, it will balance your, okay, EH, this Hall voltage will balance your this force EBB. Okay. So this is E. Now if I say current is IX, if current is IX, okay, then I can write this is a VX, and I can write this is a BZ. So this is VX, this is a BZ, and this EH is what? Y direction. Okay. So now I got a Hall electric field as a Vx upon Bz. Okay. Now Vx is the velocity which generally depends on our current, what current I'm applying. So I can write my Hall electric field is proportional to instead of Vx, I can write what? Jx, current density, and Bz. Okay. And if I further solve this one, okay, so my EH will be what? My EH will be simply RH JX BZ. Okay. And this RH is called Hall coefficient. So Hall coefficient is equal to EH, okay, JX BZ. Okay. Now you can put the values of Jx and Bz. Okay. EH value you already know. What is the value of EH? This is Vx Bz. Okay. EH value is what? Vx Bz. And what is the value of Jx? Jx is the current density. Okay. Jx is the current density, which is equal to what? Ne Vx. Okay. So I can put Ne Vx, and you have already BZ here. So BZ cancel, VX cancel. So now what I get? This is a well-known expression for Hall coefficient. RH is equal to what? 1 upon NE. Okay. Now, by measuring this Hall coefficient and by measuring the sign of the Hall coefficient, okay, you can know whether your sample is a N-type sample or P-type sample. Okay, if you're getting RH, okay, if it is the electrons, if you're metal, then RH will come negative. Okay, and if you sample is P-type, then this the sign of this RH will come positive. Okay, and if you can measure this Hall coefficient, you can know the carrier concentration in your sample. Okay, so this is the one formula of Hall coefficient. Okay, there is the one more important formula which generally we do when we perform our experiment. Okay, that is called Hall voltage. Okay, now if you ask you write the formula for Hall voltage, okay, can you write the formula for Hall voltage? Okay, so now if I want to write the formula for Hall voltage, what should I do? So my EH is what? What is the relation between EH and VH? If this is the breadth V, if it is this B,
Del V by del P.
so my E is what? Minus del V upon del X. Okay. Now, how much is delta X? Delta X how much? The distance is how much? Into
B.
B. Okay. B, and voltage is how much? Whole voltage. So I can write this much. Okay. Now I need Hall voltage. So Hall voltage will be what? EH upon B. Okay. And EH I already know. EH is what? VX BZ upon B. Okay. Right and wrong. Okay. Now can you change this now? Can you change this formulas? Okay.
VH upon B नहीं होगा. EH is equal to VH upon B.
हमारा क्या होता है? V equal to ED होता है ना? हाँ, सही. Okay. So V equal to ED होता है. So this means this will सही तो बोला. V equal to ED होता है VH by B. VH by B, correct. Okay. So VH by B. So now VH will be what? B into EH. Okay. Now I can write this is a VX BZ B. Now let us simplify this more. So if we simplify for this, okay, I know what is my JX. JX is what? IX upon area. What is the area? What is the
L.
area?
LB. L into B.
L into B कैसे? क्रॉस सेक्शन एरिया कौन सा है? क्रॉस सेक्शन एरिया क्या है?
L into T.
B into T ना? B, L is the length. B, this is your sample. Current flows through what? Cross section. This is a cross section. Suppose this is okay. So current is flowing this cross section. This is the length. Okay. This is the length. This is the breadth, and this is the thickness. So this is the cross section. So this is what? B into T.
Yes, B.
B into T. Okay. Good. And this is a very important concept. Okay. When you're using problems, you should know how to apply this formula. So this is BT. Okay. JX equal to BT. Okay. Now how can you bring this RH here? Can you bring RH here? So just now we told what is RH. RH was equal to what is the value?
By any.
In terms of JX, what is the value?
EH upon JX BZ.
JX BZ upon?
EH upon JX BZ.
Okay. So we have EH, okay, EH upon, okay, JX BZ. Okay. Now you can put these values, okay, EH values here and see what is coming. Okay. So if I put EH value here from here, okay, so I'll get VH by B. Okay. And if I put a gx value, I'll get ix upon bt, and this is my bz. Okay, so let me simplify this more. Okay, so let me write this here. It is cutting here, so this is vh. Okay, bix bt bz. Okay, so this is the relation here, and your bb cancel. Okay, now you get rh equal to what? vh into t into ix into bz. Okay, so your v hall voltage will be what? It will be rh ix bz upon t, and this is the a well-known formula what you use in lab experiment when you do perform all that experiment. Okay, so experimentally what you do? Okay, so you know the thickness of your sample. Okay, you know the thickness of sample, you know the magnetic outside, you are applying current sample that you can measure experimentally. Okay, you are applying magnetic field externally that you can measure using Gauss meter. Current you can measure also, current you also can measure. Thickness you know the sample. Now when you apply this current, you will measure in lab, you will measure hall voltage. Once you know the hall voltage, you can know what is your hall coefficient, isn't it? So in lab, you apply current in sample, you apply perpendicular magnetic field, you measure current in the sample using ammeter, you measure magnetic field using Gauss meter, you know the thickness sample, you can measure thickness sample by a screw gauge or one caliper, whatever you use, you know thickness sample, you apply current, you measure the voltage between this point, 2 points perpendicular, that is your hole voltage, and once you know the hole voltage, you can calculate what is your hall coefficient, and once you know the hall coefficient, you know the type of carriers, and you also know what is the carrier concentration. Okay, I hope you understood what I told here. So this is your Hall effect. Okay, so this is we have derived using classical theory. Okay, now we have to solve some problems because very good problems came on exam. Okay, based on this one. Okay, so let it give me 5-minute break, and then we start solving the problems. Now let us solve some previous year problems. Okay, they are very beautiful problems. Okay, on Hall effect. So now what geometry I gave you in the theory, that geometry you have to remember. If you know that geometry, you can solve any question on Hall effect. Okay, I have seen last 20 years papers. If you understand the geometry, how we are applying current, what is the cross section, okay, what is it, where is the thickness, if those geometry of sample you understand, you can solve any questions. Okay, so let us give me one problem which came in December 2016, net JRF 2016. Okay, net JRF December 2016. Okay, so what they're doing, they have given you sample. Okay, and they are saying that the length of the sample is A. Okay, so length is slightly longer. Okay, length is longer. Okay, and they are saying this is the breadth is V, and thickness they did not give anything. So thickness you can assume because the sample should have some thickness. So and what are they doing now? They are applying a voltmeter V. Okay, and now what they're doing, they are measuring the hall voltage across the opposite ends, and they say the hall voltage is V1. Are you getting my point? They have given cross section A, B, thickness you can assume whatever you want, T, W, whatever you want. Okay, now what they're doing, same sample they have rotated. Now they are rotating like this. Okay, and now they are applying voltage, and they are applying same voltage. Okay, now this time this length is A and this length is B, and again they are measuring the whole voltage V2. Okay, now they say the ratio of V2 upon V1 is 2. Okay, so they're saying find out what is the ratio of A by B. Okay, so do it please. कैसे करोगे? How will you do this? Are you able to understand the question? Your sample, you're applying same voltage, just you change the orientation, and again you're applying. Okay, magnetic field is always perpendicular to sample. The magnetic field Bz is always same values. Okay, they are not changed. Everything is same, and now they are measure the ball voltage, and they know measure the ball voltage, and they are giving this ratio. Okay, so tell me when I'm measuring whole voltage in this geometry and in this configuration, what will be change? Where will be the change?
Cross
If
section.
so if cross section is changed, so what will change? So let me write the formula for first VH. Okay, what is the formula for VH? Okay, just now I told you what is the formula for T above RH and
IXBZ.
IXBZ. So now what is changing? If I change, so RH is constant for given sample, because RH is equal to 1 by NE constant. BZ you're applying constant, thickness is constant. So what is changing? Current. Obviously current will change. Cross section is changing, the current will change. If I'm flowing current, Jx equal to what? Ix by A. Now if cross section is changed, obviously your current will change. Okay, so let me tell now the say one time you're getting VH, so say one time you're getting V2, so say current is I2. Next time you're getting V1, so you say current is I1. You obviously current will change. Why current will change? Tell me why current will change? Because resistance of sample will change. If you're measuring resistance like this, or if you measure resistance like this, which will be having higher resistance? Resistance depends on what? Wire
Inversely proportional to area.
and proportional to
Length.
so here length is more, na?
Yes, sir.
Now current is passing through here to here, so the current is facing more resistance. Here the current is going from here to here, distance is short, so obviously current is facing less resistance. So obviously when you orient this one, the current will change. Resistivity of sample is constant, that is a material property. Resistance is not a material property. Resistance depends on dimensions, so your length is more, your resistance is more. Okay, so in one case you have V2, in other case you have V1. Okay, now just calculate what is the ratio of V2 by V1. So if you calculate V2 by V1, it is come out I2 by I1. Okay, now how to calculate I2? V2 by V1, I2 by I1. Okay, now V2 by V1 is already given in the question 2. Okay, ratio of V2 by V1 is already given. Now you want the ratio of I2 by I1. So what is the value of I2 and I1?
So J into A. J into
J इंटू ए करने की जरूरत क्या है भैया? I को आपको चाहिए I, वोल्टेज दे रखा है, दोनों केस में वोल्टेज V है, तो क्या हो जाएगा? वोल्टेज तो V है, R2 रेजिस्टेंस R2, and here voltage is same V, current is what? V by R, resistance R1, V we cancel, so this become what? R1 upon R2. Okay, now you know R1 by R2, so you are getting now whole voltage. This is whole voltage. Okay, so whole voltage 2, whole voltage 1. This is your R1 by R2, and R1 is what? R is what? Rho L by A. So now rho is same. L in first case, you have length is A. Area is what? Area is what? Cross section is what? B into T. If you assume thickness, in first case you have this cross section B into A. Are you getting my point? This cross section. And second point again ratio is same. Now length is B and cross section is what? Cross section is what? In this case, what is the cross section?
80.
80. The length is A and thickness is T. Okay, this is one, length is A and thickness is T. This is the cross section. Okay, this is my cross section. So this is A into T. Okay. Now VH1 upon VH2 upon VH1. Okay. Now TT cancel. Okay. This cancel. So what is coming? A square upon B square, and this value is given 2. So A by will be what? Root 2 by 1. Okay, root 2 by 1. The ratio of A is to B is root 2 1, and this is given as option D, and this is the correct answer. Okay, are you comfortable what I'm doing here? No response. I don't know somebody sitting or not. Okay, so so this is the
Sir,
beautiful. Yes.
sir, there was a formula Vx BZB.
So we don't require ना we in question में हमको V2 even दे रखा है. ठीक है?
No, sir, VH equal to Vx BZB. The Vx is the speed of electron.
हाँ.
So that will be same. BZ is same. So
So why Vx will be same? Vx depend on current, na? Vx depend on current density. So if current is changed, so Vx will change. Your current is what? Jx equal to NEVx. Velocity means flow of charge, and flow of charge depend on what? Current.
yes, sir.
Now voltage same. So current cannot be same because the resistance changed. Okay.
Okay, sir.
So you do this one, okay, and then you write this one. So this is the correct answer. Okay. Hope you understand the question. Okay. Now, if you still have some confusion about this sample, okay, and then there is no other option. Okay, you have to take some rectangular sample. Okay, you have to take some rectangular sample in your home like this. Okay, and you say this is length, breadth, thickness, and this is a cross section, and you do it yourself. Okay, when you do yourself, then only you understand what I'm saying. Okay, and your all the questions of Hall effect, it depend on this geometry only. Okay, you need to understand the sample geometry. That's why in the beginning of the class I told the geometry what I'm drawing, that is very important. Okay, so let me solve one more question. Okay, this came in 2012. Okay, so they're saying a magnetic field sensor. Now Hall effect can also be used to sense the magnetic field. Okay, because if we can measure Hall voltage, obviously we can measure the magnetic field also. If we know the current, if we know the Hall voltage, we know the current, we know the Hall coefficient of sample. So then indirectly we can measure magnetic field also. Okay, because all these quantities are related. Na? If we know there are 4 quantities, if we know 3 other we can calculate. So we know the VH, just now we did VH is what? RH, T, then IX, BZ. Okay, now if I have a sample that is known to me, okay, so in experiment I'm measuring the Hall voltage. I know this RH of the sample, I know the thickness, I know the current, so I can calculate, I can measure the magnetic field also. Okay, so they say A magnetic field sensor based on Hall effect is to be fabricated by implanting as silicon film of thickness 1 micrometer. So they given a silicon film, and the thickness they are given 1 micrometer. Okay, that is 1 into 10 raised to power minus 6. Okay, thickness sample is given, and they are saying the specification require a magnetic field sensitivity. Now, what sensor we are require? The sensitivity is given. The sensor sensitivity requirement, or the sensor should able to measure 50 millivolt per Tesla. 50 millivolt per Tesla. Okay, so I have a sample. When I'm applying magnetic field, so when I'm applying 1 Tesla of magnetic field, it should give me whole voltage equal to 500 millivolts. So sensitivity is given. Okay, and a current is flowing. Okay, current is flowing. The sample is equal to 1 milliampere. Okay, so what they're asking, the average carrier density. Okay, what is the average carrier density? Okay, calculate what is the average carrier density. So what should I do?
सर RH का फॉर्मूला निकाल लेंगे, कैरियर डेंसिटी 1 by NE.
Very good. Okay, you measure RH 1 by NE. Okay, so first you measure RH. Okay, RH is, how can you measure? So you know RH is equal to BH thickness IX BZ IX. Okay, and sensitivity they already given, BH by BZ is already they given. Thickness you know, IX you know, you can know RH know, you can calculate the electric field. Calculate and tell me the value. What is the answer?
1.25 into 10 to the power 22.
Yes. Okay. So if I calculate, so we get 1.25 to 10 raised to power 22 per meter cube. This answer should come. I hope all of you are getting this answer. Okay. Per meter cube. So this was today's class. Okay. So now only what is remaining. So what I'm doing actually, that is the theory part. Okay. So question asked only basically concept wise. Okay. 1 or 2 questions they ask from this portion also. So major portion of questions comes from quantum theory, field electron theory of quantum. Okay. So one portion more remaining, that optical properties of metal. Okay, that we will finish tomorrow, and probably from tomorrow itself we'll start quantum free electron theory. Okay, and quantum free electron theory is very easy. Okay, the conceptual part you are already familiar. Okay, like what we have done, the density of states, k states. Okay, similar lines. Now we will instead of here we are using classical theory. Okay, there what we'll do, there we'll use Schrodinger equation. Okay, and by using Schrodinger equation, what we'll do, we'll apply periodic boundary conditions, and we'll see how the when electrons are in the solid, okay, they behave as k waves. Okay, so what are the restriction of their k value, and they will come out same what we've done for our lattice vibration. Okay, once we know the k things, rest of the part is very simple. We can know the density of state for electron once we know the density of restricted electrons, we can calculate the energy to system. We can calculate, once we know the energy system, 1D, 2D, 3D, and we can calculate their similarly we can calculate the specific heat of solid also. Okay, so many questions came from this quantum field electron theory. Okay, that's we'll start from tomorrow. Okay, now if today's portion I didn't get any response, okay, if any question you can ask me now. What we've done today? Any question from today's class? So today we have derived Whitman French law. Okay, so we already know electric conductivity classically, and we have calculated thermal conductivity, and then we have just simple derivation was there, and we have calculated we have derived the Whitman French law. Okay, so if there are no more questions, okay, so I'm stop. हाँ बोलिए.
सर आपने एक पहले एक बोला था कि इलेक्ट्रॉन ही एनर्जी फ्लो करने का मेन मेटल के मेन सोर्स है. तो सर पिछले दिन हमने पढ़ा था कि स्पेसिफिक हीट इलेक्ट्रॉन की जो स्पेसिफिक हीट होता है वो वेरी लेस कंट्रीब्यूशन होता है.
तो ट्रांसपोर्ट अलग थी ना, ट्रांसपोर्ट अलग चीज है, स्पेसिफिक हीट का डेफिनेशन अलग चीज है. स्पेसिफिक हीट क्या होती है
सर? हीट पर यूनिट टेम्परेचर में कितना हीट
हीट अब्सॉर्ब करने के लिए, ठीक है.
हाँ.
तो अभी भी हीट तो अब्सॉर्ब तो एटम ही कर रहे हैं, वाइब्रेशन ही कर रहे हैं. ओके, अब क्या, लेकिन अब मेरे पास ये टेम्परेचर, यहाँ पे एक टेम्परेचर है, यहाँ पर टेम्परेचर है, यहाँ टेम्परेचर है, ये टेम्परेचर फ्लो कैसे करेगा यहाँ से यहाँ तक?
अच्छा ठीक है सर, समझ गया.
तो ये इलेक्ट्रॉन यहाँ है, वो यहाँ से टकराएगा, वो यहाँ का एनर्जी ले लेगा, फिर जाके यहाँ टकराएगा, ये एनर्जी यहाँ दे देगा, फिर ये आगे एनर्जी दे देगा. इस तरह का वो हीट ट्रांसफर करेगा, तो टेम्परेचर चेंज होगा इधर का. ठीक है, फ्लो होगा हीट.
ठीक है सर.
So I'm stopping here.
थैंक यू सर.
Thank you. How to stop this one?